Um, today, Carter, you're doing your thing?
Yeah.
Okay. So I had a massive grading marathon yesterday and graded your fraction classes. So I tried to give you a lot, at least to try to pinpoint where specific issues might be, and also if I was feeling really ambitious, I would actually even try to fix your code. If I didn't do that, oh well. So your job is twofold. If unless you are perfect, and I think there were only 2 perfect classes in the class. So unless your class was perfect, job 1 is to get all of those things running, functioning correctly. I will post my test program so that you can link against it and run it and test it using my test program. And then the second part of your job for the next homework will be to get those assignment operators. I judge that second task as being pretty straightforward. It's really a syntactical exercise, and you should test all of those things, but I don't think it's going to be terribly difficult. I think for some of you, the hard part is going to be making sure that your add function works, making sure that greater than, less than, yada, 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 all those things work. So in a way, you sort of get 2 chances to get this class right. As I was grading, I realized that I had a couple of typos. And so a couple of you left out the decimal operator, and I realized that in the online version, I had put it in there, but in the downloaded copy, I had left it out for whatever reason. So for that, I apologize. And if you got points taken off for that, I actually went back through this morning and fixed that and gave you the points back. I didn't realize it till this morning that was the mistake that had happened. Similarly, again, not really sure what happened here, but the downloaded reduce.cpp file that I provided had a typo in it. And so I fixed that as well. Not many people got nailed by that, but as I was checking this other typo, I was like, wow, I wonder if the other file is okay. And see what happens, this is the danger of maintaining the web page and then these separate files, right? So I make the changes on the web page and I forget about the files. And so that's my bad. Another typo from possibly Monday. The print function had an or in it. It should have had an and in it. Yep. I actually docked you points for that because you could have caught that really easily just by testing. So I left that alone. And then I had some further thoughts. Somebody in here wanted to use decimal for greater than, less than? Yes. Well, I actually thought about it a lot after you'd made that comment, and I think it's actually better.
It is better.
Let me tell you why I think it's. Why do you think it's better?
It just makes you have to do a lot less coding. It's really
No, that's not why it's better. Does anybody have an actual reason why it's better? Can you think of an actual reason?
Is efficiency not a good reason anymore?
I would argue that DES is actually more expensive than the other way, because doing a division is much more expensive than doing a multiplication.
Do you have like a greater range in numbers because you're multiplying?
Oh, because it's doubles?
Exactly, yeah. You have to do A times D and B times C, and you risk overflows, right? You suddenly can't use the full range of unsigned ints. So then I'm thinking, well, can you use the full range of unsigned ints in decimal? The answer is yes. If you're going to do a double precision decimal, how many digits of precision do you have? Does anybody remember? How many decimal digits of precision does a double have? 16-ish. Let's go 15 and be conservative. 15. What's the smallest decimal you can get from from one of these fractions? Does anybody know that?
Like 1 over 4 billion?
1 over 4 billion,
It's whatever the
roughly 10 to the minus 10, maybe? 10 to the minus 10, which fits nicely into 16 or 15 significant digits. So it's more expensive, but it preserves the range issues, the overflow issues. So if I do this assignment again, I will let people use DES. So thank you for pointing that out, Dylan. Not completely wasted effort, however. It's an interesting programming exercise to try to do it without DES. So it's not wasted effort. It requires thought and logic to make it happen. But from an actual sort of computational perspective, I believe that DES is the right thing to do. So thanks for that, Dylan. Any other questions, comments? Or Kendall, or whatever. Did you do it too, Kendall?
Yeah. I was wondering if your office showing me.
Oh, I thought it was Dylan. My bad.
I had similar problems.
All credit goes to Kendall. Excuse me.
So,
Emily.
to work on homework 7, instead of like copying all my files out of homework 6 into homework 7, which is what might have been easier, I copied them all within homework 6, and then rename them in homework 6. Now I want to get them in homework 7.
Yes.
Oh, wait. So are you trying to copy, like, what I did was I just copied my entire homework 6 folder? That would have been smart. However, I copied it, the files within homework 6, and then I did made a bunch of changes, and now I want
It's not really too late, though, Emily. I think still the right thing to do is that way. So let me just show you that really quickly.
Or you can go on the math app and do some physics.
That's what I was gonna
Yeah, but let's do it this way.
Sure.
I like the point.
So let's say I'm in my homework directory, and I'm ready to write my new fraction class. I can do cp-a h06 fraction class to h07, like that. And that will create a new directory, and the contents of said directories, h06- fraction class and h07, will be identical.
Okay, and then I can.
And then you can mess around with what happens in there. Yes.
As a question, what's the difference between the dash A and the dash R?
There's really no difference. The reason I use dash A is if you're copying a directory to another directory with the same name, it's smart and it won't replace files that are the same. So dash A is a little bit smarter than dash R, but it's really useful for super large trees, that you're copying, because say you copy a massive directory with lots of files in it over to another directory, and then you make a couple of changes in this directory, like you forgot, which I do all the time, and then you copy it again, it'll just grab those couple of changes and do that. Other questions? Ask me anything about Unix.
What's your favorite part about it?
The command line. Yes.
Okay, so last time I did put my makefile in before I wrote my main, and then my makefile wouldn't work, so I had to compile it manually.
You had your makefile in, but you hadn't created main yet. Yeah, it's just because make is really just a recipe for building this thing, and one of the ingredients is main.cpp.
Right.
And if it doesn't exist...
Well, I wrote it, but I wrote it after I put the makefile in, and so then I was in fraction.cpp and I tried to do :make.
That shouldn't have been a problem.
Okay.
So the order in which you create those files, makefile and then main, or main and then makefile, is irrelevant. So if you're still having that trouble, I would be happy to look at it afterwards.
So you first have to use the E command and the pound command to switch back and forth between tabs and forward. I guess when you're using the pound, so how is that different from the pound?
Okay, so I often enter a directory. Oh, my hands are not on the home keys. Okay. Wait, really? That's so bizarre. When I type an L, I get a 3. Oh, numlock. Laptop. Anybody know how to unnumlock?
Is there a function that unlock on the place?
Got it. Yes, unnumlock. Don't ask me about numlock though. Okay. Often when I go into a project like this with several files, I will literally just do vim star.cpp star.h and makefile and get them all in there. Okay, and then you can do ls and you can see the buffers. And I can switch, and I think we've talked a little bit about this. I can switch to say fraction.h by going to buffer 3.
Oh.
And I can go to the makefile by going to buffer 4. And at the same time, it keeps track of the last file that you were in. And if you want to quickly toggle between files, like I often do between main and fraction.cpp, what I would do is first visit those files. So let's go to main, and then let's go to fraction.cpp. So the last 2 files I've visited now are main and fraction.cpp. I can now toggle back and forth with this B #. And I use that all the time, as you have well noticed. B by itself won't do anything, so I'm not sure what you're saying.
Yeah.
Okay, got it. Other questions? On the agenda today, I want to talk about this constant keyword. I hoped to talk about it last time. Just didn't quite get there. It's okay. I think we're okay on time. We've got a little bit of slack leading into the second exam. I want to write a negation function. I wonder if I can type on this. It would be easier to type, actually. It's not very visible, though. I could. Any ideas how? I'll just write it. Oh yeah, maybe do like 14 or something, and maybe even bold it. Thank you. Oh, and you know what I should do is do it in a fixed width font, like Courier or something. Courier? Anybody? There it is. Yes. Okay, so let's do this. Nope, that didn't work.
Oh, because it's for every page.
Oh, that's really stupid. Okay, back to writing then. So let's consider this negation function. Some clever person might want to try. Remember what negation does? It toggles the sign of the fraction. So if the fraction comes in and it's negative, it goes out positive. And if it comes in positive, it goes out negative. The numerator and the denominator are unchanged. So this clever person said, okay, let's look at the sign. If the sign is true, so right, if sign is true, then this part will happen, right? Then make sign false. Otherwise, make sign true. And return fraction, numerator, denominator, sign. What's wrong with this?
It's changing.
It's changing sign in the calling object. Bad, bad, bad. This is damaging. This is damaging the calling object. Remember how this thing would be used. You would have a fraction, say f. Let's call it -1/2. And maybe you have another fraction, g. The way that you would call this is g is equal to f dot negation. Oops, negation. With the idea that a completely new fraction object is created with the opposite sign and then placed into g. There's literally no reason to change f, and in fact it's bad to change f. But that's what's happening right here. You're changing f. Does everybody see that distinction? So the clever person not wanting to declare a new variable and use that new variable to create the new fraction, just use this existing variable from the object itself and wrecked the object. The object came in, it was -1/2, and it left as 1/2, and that's bad because the user of your class, that's not how this function is supposed to behave. This is a really common error, especially for large classes with lots of data. And so C++ and Bjarne Stroustrup, the creator of C++, added some features to the language to help protect the programmer from themselves. And that leads us to something called the constant keyword. Careful/thoughtful use of the constant keyword will prevent these errors. There are two main uses. One on arguments to functions, and two on member functions of classes. And these are philosophical in nature. It's about looking at what you're doing and thinking about what's allowed to change and what's not allowed to change, what should be changing and what shouldn't be changing. This is something that all practiced C++ programmers get in the habit of doing when they write a class. They scan through and they think about what's changing, what's not changing. What do I want to allow to change? What do I want to allow? What do I not want to allow to change? So let's be a little bit more specific here. I'm going to label these, instead of with dashes, I'll label these A and say B. All right, so A, if the function doesn't assign a value to a particular argument, then make the argument constant. What would be an example of this? Well, a really simple example would be the add friend function. Remember how add works? It takes in these two fractions. It computes the sum of the two fractions, builds a completely new fraction that is the sum of f and g, and then returns it back to the calling program. Does add change F or G?
No.
It doesn't. And a safe, careful programmer would note that. And when they declare add, friend, add, well, let's look at the original prototype here. So, fraction, not friend. Second time I've done that. Okay. Add fraction, fraction. Now you might be thinking, well, you know what? Add can't change these guys anyway. Why not?
It's not the public.
Eh. Pass by value, pass by reference. Sound familiar? These are pass by value parameters. So add could change the two arguments inside, but when they get back out, that's not going to happen. Okay, so those changes aren't going to be reflected to the calling function. So you might think, well, oh, we never need the constant keyword for function arguments. We can just pass by value. We can just pass by value. Unfortunately, that's not a good solution. Can anybody think of, do you remember how pass by value works?
It takes the copies of something and uses those.
Yeah, it takes the argument, creates a copy of it for use inside the function. So why would pass by value why might that be a bad thing to be stuck with?
Because if you change your original for whatever reason, it doesn't change your copies.
Not so much that. Em, did you have a?
Like if we wanted to print those values? Or
I'm thinking more about efficiency issues. When is copying inefficient or expensive? Yeah. So what if your fraction class, instead of just having a simple numerator and denominator, which is relatively inexpensive to copy, what if instead your fraction class had 600 gigabytes of data in it? And all you wanted to do was pass it into a function to say, search to see if some particular word was in there. You're going to make a copy of 600 gigabytes of data, pass it in there, search and see if the word's in there, and when you're done, you're going to leave. That's wildly inefficient. So yes, pass by value can protect your function arguments from inadvertent changes, but if you're stuck with pass by value, you're stuck with potentially a very inefficient situation. So the downside is pass by value may force the creation of a very large copy. And so it might be really inefficient. So what if? How can I avoid making a copy of an argument? Pass by reference. But then how can I protect myself from making changes? I can make a constant pass by reference argument, and that's where I'm headed. Pass by reference is cheap since no copy is made, but dangerous because you now have access to the original data. And again, all of this is really, we're talking about programming errors. Right? If you have your wits about you and you're careful, you don't need constant keywords. You don't need them on arguments. You don't need them on member functions. You don't need pass by reference, pass by value. You can always pass by reference if you want, if you're careful. But part of, as I've mentioned in here before, part of writing a good programming language is dealing with human psychology and human fallibility. And so the language has these built-in features to sort of protect programmers from themselves. So the solution here is to do constant pass by reference. And in fact, you should always do this. For programmer defined classes. Like fraction, for example. There's another issue that I'm not getting into right now. It's more for the advanced course. But there are certain kinds of objects that you can create where when you pass them by value into a function, they don't get copied correctly. The copies aren't made correctly. And then things just really get broken. There are ways around that. You have to build something called a copy constructor and an assignment operator overload and yada, 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 so you can get around these issues. But a 100% certain and safe way of passing a user-defined object into a function is to pass by reference. And if you're afraid that you might damage it by doing so through some accident of programming, pass it in as a constant reference. So for example, the new and carefully written add function might look like this. Oh, and I'm sorry, this has a return type of fraction. Constant fraction, not frank, fraction, ampersand, constant fraction, ampersand. That would be the correct way to prototype the add function, to define the add function, or declare the add function, excuse me. And then down when you write the add function, so later in fraction.cpp, it would look something like this: fraction, add, const, fraction, ampersand f, const, fraction, ampersand g, and then all of the stuff that you would normally do, that you would normally have in your add function would still work. Nothing inside changes. But what will happen, come on, there we go. But now the compiler will notice statements like this. And it'll say bad. So f is coming into this thing as a constant argument. Any assignments to any part of f will be flagged and will not compile. let's talk about constant member functions. So as we pointed out earlier, the negation function, the absolute value function, the desc function, the print function, none of those guys should change the calling object, right? How can we express that to the compiler? We use the constant keyword in the following way. So let's pick on negation again. Let's see, negation it returned a fraction, and it was called negation, and it had no arguments. I think that's correct. And what you do is you slip in a little constant keyword right here. This declares negation a constant member function. And what this says is calling the negation operator, or the negation function, will not change the object. Calling negation will not change the object. That's what you're telling the compiler. Now, if you go back up to the top and you look at how I started this discussion, way back up here, if this guy is declared a constant member function, it'll blow up right here. Because you're trying to assign a value to the calling object. Let me take that guy, rewrite it so that you can see what happens in fraction.cpp. In fraction.cpp, the syntax is as follows. You would have something like fraction, which is the return value, then the scope resolution operator, and then the constant keyword, and then everything in here is the same. Same as before. Let me show you an even subtler way in which this protects the programmer. Many of you wrote your subtraction functions as follows. Let's see, fraction, subtraction, fraction, f, fraction, g, and then you just returned add f g dot negation. Does that ring a bell for some of you? That was the most efficient way to do it. You spend all your time building add, and you get negation working, and then you get subtraction for free. You don't have to think about it. Thank God. Now, subtraction. If we're going to use this new constant keyword stuff, how should I change this guy to be more careful? What should its arguments be?
Well, inside of like the function.
I'm talking right here.
Yeah, it should pass those by reference.
I should do constant pass by reference, right? So I should stick in two constant keywords here and here. And what else?
The ampersand.
And the ampersands here and here. Let's pretend I do that. If I don't have the constant keyword on neg, it'll yell at me. Why?
Because neg will change something.
Neg might
Or
change
might.
something. Neg might change something. So now the only way this will work now compiles is if the programmer has explicitly Now, it may be that the negation function that you wrote doesn't change anything in the calling object. But if you don't tell the compiler that it's a constant member function, this still won't compile, regardless of whether the calling object is changed by negation or not. So it's all intertwined. And it starts very simply. You go through your class and you look at all the arguments and you decide which should be constant and you make them so. And you look at all the member functions and you decide which should be constant and you make them so. And then if you're doing something like this, you're protected. You're not going to change your objects by accident.
Can you give an example of something that we wouldn't want a constant for?
Sure. So let's go. You know what? I'm going to pause there, Danielle, and let Carter do his thing. And then my plan is to actually go through and build an entirely new class that we haven't talked about yet, something called a set class. And we'll see several examples there. Carter, come on up and do your thing. Do you need the computer?
No, yes. Just Google Maps. Not my email.
Okay, you can start talking and I will get Google Maps up.
Okay. So, my question was, how does Google, or any ISP, locate you based on your internet connection? And
just click this little dot right here and it locates you.
yeah, when you allow.
Might take a second.
No, you have to allow.
There we go. Right at the west end of Olin Hall.
Which is kind of creepy.
Super creepy, yes.
But it's okay. It's Google. We trust them. Okay, so there are a couple things they do. One is they look at the IP address. And we've talked a little bit about IP addresses here, so I'll go over it shortly. It stands for Internet Protocol, and it's a unique number that allows identification on the internet, so you can send things over the internet and receive things over the internet. Then ISP is your internet service provider. So there are a bunch of different types of IPs. There's public IPs, which is like a router, and it shows your public IP to the internet so that it can receive things, and then your laptop or your computer has its own private IP, which it doesn't show the internet doesn't get to see because it's a little safer. And then there's also static IPs, which are like businesses have static IPs which never change. They just have their IP forever, because if they want to link servers, it's better if they only have one IP so they don't have to like change it. But what like homes homes have dynamic IPs, which internet providers will periodically recycle IPs to homes, and it makes using an IP kind of hard to track locations. But sometimes you can. It's much easier to track static IPs. So Google does look at your IP, but another thing it does, which is really cool, is it's called geolocation or Wi-Fi location. And before I talk about them, everybody knows Google's vans, the street view vans that were mapping all the streets. Well, they had an ulterior motive, which we didn't know about, or at least I didn't know about, which was they measured the signal strength of different Wi-Fis in the area that they were and made their own little map of Wi-Fi strengths all over the world. And so now what we just did with Google, here, I'll refresh it so you guys can see it again. So when you click this guy, Just kidding, it doesn't do it anymore. But what happened was it popped down here and it said allow, and what it was allowing is Google is asking for your Wi-Fi strengths, like the strengths of the different Wi-Fis your computer sees. And so if you allow it, Google can look at that and, using the map that it made with its Google streetcars, figure out where you are, which is
Sort of triangulating.
yeah. And then a third thing they can do is they can ping your phone, and your phone has a lot of like GPS, cell ID, and Wi-Fi, and it can also use your phone to help track you. But it's mostly about the computer, and it only works if your computer does wireless. If it doesn't, they just try to use an IP. And then finally, so I was looking for some opposition, and there is a GPS Act going through government, which is trying to cut down on the amount of location information people can keep on you. So there is some opposition to all this information about people.
Questions?
I think what you kind of went into it with that there was an ulterior motive to Google.
Mhm.
I think they got mad at Google because they were also downloading stuff from people's unsecure networks.
Yeah.
So that was kind of
Yeah, I remember I think it was them and Apple both got into trouble for, having their vans move about without people really knowing what was going on.
So when they did those, tracking those networks, those networks have obviously changed since they drove their vans around through town.
Yeah, it's true. They do drive vans around periodically, so it's because they want to update all of their information. So it is true. Sometimes they'll get it off, but it's fairly accurate. And a lot of networks don't change because a lot of homes just don't care. Like my mom's crazy and she changes it once a month, but most people don't do that.
So if you choose to say unenable location services, is that just you kidding yourself because they can find you anyway? Or do you actually
Oh, well, you don't give them your wireless strengths.
Okay.
So they can't tell where you are.
But if you're running, if you have Android in your pocket right now, which I know some people do anyway, I do. If you have Android in your pocket and you just sort of say yes to everything, then you're just a continuous font of information for Google.
But you can turn that off though.
I can, yes.
Yeah,
I
but I
choose
guess
not to.
yeah,
I don't care.
That's true.
But Google. So if I take that laptop to the other end of the building, that little blue dot will move to the other end of the building too.
Yeah.
And what's I think the Street View cars have done sort of some low-level stuff, but I think they're probably getting most of their location information now from these little tracking devices we carry around in our pockets. Because clearly the phone has GPS and knows where I am, right? So I go to Google Maps and let's say I'm using the Wi-Fi on my phone, right? So probably the Wi-Fi on my phone right now is connected to that same access point as that guy. So, and I'm running Google services and I'm letting Google know whatever they want to know about me, because again, I don't care. And it has my location, and it's connected to that wireless transmitter. So it knows that I'm within about that far of this wireless transmitter. And then it does use some of that auxiliary information of overlapping wireless access points and stuff to really narrow it down. For example, we saw that the bubble of probability expanded there. The only thing I can think of is that one of the wireless access points that laptop was listening to fell out of range for some reason, and so the triangulation got worse. But yeah, the phones can sort of tattle on the wireless access points. So my phone, Google knows where my phone is, and Google knows that I'm attached to that access point. So now Google knows that access point is near this phone. It only needs to find that out once, right? And then puts it in a database, and that access point is near this phone, which has those GPS coordinates. It only needs to know that once.
This is, of course, granted you told your computer that's your phone.
No, I'm talking about the one in the ceiling.
Oh, but I mean, Like, it has to know that this laptop and that phone are the same person.
It smells like a portable window.
Yeah, but
No, I'm not. The laptop's not in it anymore. So.
Oh, you're just talking about your phone.
So now it knows that anybody that connects to that access point, right? So my phone has told Google where the access point is. Now anybody that connects to that access point has to be within a certain range of this physical location, right?
Yeah.
Okay. It's amazing what kind of sort of accidental information you're sharing with Google and other people, isn't it? Anyway. All right. Thanks, Carter. I don't know what anybody would say. Yeah. People keep talking about the founding fathers. Pretty far from that. All right. Boy, there's one other thing I was going to say. Oh, not only does every device have this IP address, but in fact every device has something called a MAC address. And the MAC address is unique. This MAC address for this computer is unique. The MAC address for the wireless access point in the ceiling is unique. So, yeah, think about that. And Google knows what the MAC address of my phone is. If I go to Google Maps, it now knows what the MAC address of this thing is. It knows what the MAC address of the wireless access point is, because that MAC address gets transmitted with every piece of information that goes away from this computer. So there are unique identifiers. Okay, let's talk about building another class. I'm going to just preliminarily introduce this idea, and then we'll finish it off on Monday. We've together or separately written two classes. We've written the complex number class and the fraction class. I want to discuss the possibility of building a set class. And I want to talk about sets of integers. Sets, you learned about them in grade school, and they're fairly boring, but they're also extremely powerful and quite useful in computer science. A set of integers could be denoted, for example, like this, capital S. We usually use curly braces to indicate a list of elements, say 3, 5, 7, 9. So there's a set. 3 is a member of this set. 2 is not a member of this set. And that's really all sets are good for, is membership. You're either in the set or you're not in the set. But it turns out membership is a really important thing to use in computation. It pervades computation. So having a class, can we build a class of objects can we build a class to represent sets? Of integers. So for example, let's do a few set exercises. I'm going to get another set T. Let's make it a 3, 5, 6, 8, like that. What are some questions that we ask about sets? I think way back to 5th grade. Or perhaps more recently if you're a math major. Intersections and unions, right? What's the intersection of two sets? How do you define it? Yeah, the values that are common to both sets. Elements that are members of both sets. What are some things that we can... So union, what's the union? You're in either set. So intersection is you're in both sets. Union, you're in either set. What are some things we can do to a single set? Sure, we can add an element, remove an element. I'm not going to write, I'll just talk. What else can we do to a single set? Or remove, yeah, I guess that's sort of the same thing. Add and remove. We can ask it how big it is. Right? We can say, hey, set, how many things do you have in you right now? We could clear it, perhaps, remove everything from it. We could order it, sure. Let's go back to two sets. What are some things we can do with two sets? Intersection, union, what else? I could take something out of one and put it in the other, sure. What else?
Say one set, not the other set. Maybe I'm not missing that, but that is in the first set that are in the second set.
Oh, like the complement, the relative complement. Sure. So I could take the relative complement of S with respect to T, or the relative complement of T with respect to S. Sure, relative complement. Anything else? Subset? I could ask whether S is a subset of T or T is a subset of S. Over the weekend, if you think about it, think about how you might construct a class. How would you represent the data in the class? What kinds of member functions would you like to have in the class? What kinds of friend functions would you like to have? What kinds of operator overloads would make sense for such a class? And on Monday, we'll spend most of Monday sketching this class out. And we'll be thinking about constant keywords, constant arguments, constant member functions. Until then, have a lovely weekend.